Okay, so it's a pleasure to welcome the next speaker, Miguel Navascues, who will talk about self-testing.
Thank you very much. Yeah, I'm going to speak about this paper. I think the other authors is... no, it's correct, it's correct. Cool. Okay. Well, the scenario is this one. We have two parties, Alice and Bob. They are separated. And then one of them can choose. I have a pointer. Cool. So weird. How strange. Okay. Yeah, one can choose to prepare states, right? I mean, are labeled by this X, this symbol. And Bob can conduct a measurement labeled by Y, and he will get some result. Okay. And in order to make this scenario non-trivial, then you have to assume that you have a limit in the amount of information that Alice is transmitting to Bob. So you put a cap on the dimensionality. Okay. So she's sending a state, a d-dimensional quantum state, to Bob, who's conducting a measurement. Now, it may be that having reached this point, you say, yeah, but what is he talking about? Prepare and measure scenario? What is this? What? If you think like that, probably you're a computer scientist. In which case, I have this other slide for you. We have Trinity and Neo who want to compute a Boolean function, and then using this some information given by some oracle, then using this transmittivity, they manage to find out some guess on it. And it's pretty much the same, right? I mean, it's not it's the same, it's different marketing, right, or branding, but really the same idea. Okay, you can imagine that this is a very general thing, right? I mean, you conduct a measurement and you do a preparation and you do a measurement. This is common to all experiments in quantum mechanics, right? I mean, you have to prepare something and then you have to measure something. So there are lots of things that you can model, but this framework in particular has been used to study quantum communication complexity, but also semi-device independent QKD, like QKD under the assumption that the states transmitted have some even dimensionality. And also, of course, this is the seminal paper, right? I mean, about device-independent dimension tests. You do some tests with these statistics, and you try to put a lower bound on the dimensionality of the states that are transmitted. Okay, so yeah, one thing that is important is that these scenarios are completely blind to unitary or anti-unitary transformation. So if Alice prepares the state and Bob conducts these measurements, now we conjugate both of them by a unitary or anti-unitary operator, then they will get the same statistics. How weird. It's very counterintuitive. They will get the same statistics. Okay, so this is important for what comes next, because we're going to study self-testing. So I'm going to give a rough definition. It's not, soon I will give you the right one, right? But for the moment, just to have an idea what we want. We want, based on this distribution, these statistics, we want to prove that there exists some unitary or anti-unitary that apply to some reference states, gives me the states that we're using in the experiment. And the same for the measurements. The same anti-unitary applied to these reference measurements will give me the measurements employed in the experiment. So then you will say that the experiment is self-testing these reference states. Somehow, in order to do the experiment and get these statistics, you have to prepare these states, modulo anti-unitaries, and conduct these measurements. That's the idea.
Both at the same time?
Yes.
Self-test both?
Well, it depends on the experiment. Sorry. No, you may conduct an experiment that only self-tests a few of the states, or that only self-tests a few of the measurements, or both, right? It's yeah, you can do both. Yeah. Well, we will see it. Okay. There have been like not much work on self-testing prepare measure scenarios. The first one I know of is from 2018. And again, it's in this Trinity Neo matrix thing. You have to do a 2-to-1 random access code. So the oracle is distributing 2 bits to Trinity and 1 to Neo. And depending on the bit, then Neo has to guess either the first bit of Trinity or the second bit of Trinity. And of course, if we allow Trinity to send Neo one qubit, you cannot do this perfectly. So the average probability of success will be bounded by this value. Now, in this paper, these authors wonder what happens if you saturate the inequality. And what they find is that the only way of saturating this inequality is actually to prepare these states and to conduct these measurements. Okay, that was the first example of self-testing in this scenario. Like, from a technical point of view, this experiment has self-tested 2 incompatible projective measurements and 2 mutually unbiased bases. Now, there are other important measurements in qubits, right? Like, there are measurements which are extreme, extremal in the list of all possible measurements. It's a convex set. but they are not projective, right? I mean, so that's why 2 years later, the same authors, then they came up with some tests, in the prepare and measure scenario to self-test an extreme POVM in qubits that is not projective. So in this case, it has 4 outcomes, this POVM. Okay, it's important in both cases, in both scenarios, they used a linear witness. They use a linear function of the probabilities in order to illustrate, to get to the result. Now, there's another class of papers I'm going to discuss why it's a bit different from what the other two. There's this paper that appeared 1 year later that's called Universal Scheme for Robust Self-Testing. And it's based on this observation. Suppose that you have 2 states and you want to prove that you have to certify that they're pure and you want to compute their overlap. So one thing you can do is to embed them in some scenario with 2D states, and then you assume that this one is state A, while this one is state B. And now suppose that you conduct, essentially would be like a state estimation, or a state estimation of the first D states, and you find that with the measurement 1, you can always identify which state was prepared. Okay, suppose that the statistics are such. The only way that this can happen in dimension D is that all these things are from our orthonormal basis, and also that the measurements that you're conducting are equal to the elements of the basis, to the projectors. Suppose you do the same with the second batch of states, and then you observe exactly the same statistics. Then, again, you will conclude that the state B, in particular, is pure, and that it is related to the POVM element of the second measurement. Okay, so now you combine the two, and you say, well, I'm going to prepare a state 1, and I'm going to conduct measurement 2, and the frequency of appearance, of occurrence of the outcome 1 will tell me the overlap between the two. Now, once you have the overlap between 2 states, then you can self-test if you are a bit ingenious, general state ensembles, POVMs, etc., for qubits.
I have a question.
Yes.
In the solution of this Conn-embedding problem, they also used self-testing, and they needed the robust way, right, with an epsilon permutation.
Yes.
They all satisfy robust self-testing?
Yeah, all the things are robust, yeah. Okay, the problem with this scheme is that the authors are assuming IID. They are, okay, I will explain what I mean. It stands for independent and identically distributed, and it is that they're assuming that at its experimental round, whenever Alice inputs X, she always gets the same state. And whenever Bob inputs Y, he always conducts the same measurement. So in particular, the statistics that they're observing at each round, they are identical to the previous rounds and also independently distributed. Okay? Now, they use it actually here, right? I mean, in order to make this argument I just made, right? I mean, you could think of using the first rounds to certify that this first state is pure, some other rounds to certify that this POVM element corresponds to the state B, and then you have to assume that whenever you input here 1 is the same as when you have the same effect as in the first n rounds, right? I mean, that's why you get to the overlap, right? And if you don't make this assumption, you cannot reach this conclusion. And actually, the whole paper falls if you drop the IID assumption. So you cannot really use anything of what they have developed. Now, the reason why we care, or many physicists care about these kind of things, is because real devices are not IID. So one source of non-IID is the calibration of the measurement and preparation apparatuses. So as time goes by, the devices decalibrate, and then as a result, what happens whenever you switch on some preparation device depends on which round you do it. Okay, we run through the experiment. And the second reason is much cooler, it's more physical also, is that the behavior of a measurement or a preparation device depends not only on the round, the experimental round, but also depends on what is the past history of inputs and outputs that you got. And this you can see with photon detectors. If you detect a photon, then for the next few nanoseconds, you have problems to detect a second photon. They get a bit numb for a while, right? So it depends on what happened on the previous experimental round. So you have really both things. Now, the scenario that before I describe the scenario, but only in the one round regime, right? I mean, if you go to multiple rounds, this is going to be my assumption that whenever Alice inputs in any given round K, whenever Alice inputs X, he will produce some state that will depend on the round, but also it depends on the previous history of inputs and outputs. And the same with Bob, right? Whenever he inputs Y, he will conduct a different, in principle, POVM that will depend on K. I should have put some of the dependents on some other variables. Imagine that they are there, right? Okay, so now I'm going to give you a definition of self-testing, right? I mean, for states. So we want to prove, I mean, intuitively we want to prove that the setup of Alice and Bob allows them to produce the reference states. Okay, so I'm going to do a double negation here. So I'm going to, this is the same as refuting that for every round K there doesn't exist a unitary or anti-unitary such that this holds. And now I'm going to put, answer your question, right? I mean, we have a bit of noise here. Okay. Okay, and for POVMs is the same, right? I mean, we would like to prove that this setup allows them to, the setup of Bob's allows him to conduct these measurements. And an equivalent way is to say that for any round K, there doesn't exist a unitary. Well, we want to refute this, that for any round K, there doesn't exist a unitary such that this holds, right? That would be the null hypothesis, that it doesn't exist a unitary such that this holds. Okay, the cool thing about this non-IIDs is that this problem has surfaced already in quantum non-locality. It's called the memory attacks. And people have solved it, right? I mean, in quantum non-locality, what you want to do, you want to conduct an experiment like this, and you want to argue that this experiment cannot be reproduced by classical physics. And of course, classical systems have memory. So in principle, it could be that the outputs of this experiment depend on the sequence of inputs of the previous experimental rounds. It could be that you conducted measurements in different experimental rounds. It could be that in between rounds there's communication between these two parts. You cannot rule this out, right? So what do you do? Well, I recommend you to read the paper. I'm not going to get to it's in a very bad journal, as you can see, but it's a really good paper. Right? I recommend it a lot. I think it's I don't know. Okay, so it's a good paper. So it's a paper actually about non-locality. Oh, sorry, it's a paper about non-locality, but it doesn't really matter. The ideas are very general. You can adapt them to paper and measure scenarios. And what these people do is the following. Suppose that you give me some inequality, some linear inequality. Okay, this function is linear of the probabilities. Then these people are able to design some family of n-round statistical tests. So an n-round statistical test will be some prescription to choose the inputs and outputs. To choose the inputs of each of the experiments, and also some Boolean function of all the inputs and outputs that give you a yes/no result. Okay, and yes means that intuitively it would mean that we have detected a violation of this inequality in the system, and no, it means that no, we couldn't detect it. Okay. So now, what are the properties of this test? The property of this test is that if the null hypothesis is true, null hypothesis means that for all rounds, this inequality is satisfied. Okay, for all rounds, the experiment that you were conducting. So the probability that the test outputs a detection is bounded by some number that goes to 0 and goes to infinity. Okay, so you don't want to have false positives. And the other thing is that you don't want to have false negatives, right? I mean, so in a particular case that you prepare, you have independent identical preparations of some distribution that violates the inequality, then the probability of yes will tend to 1 as n tends to infinity. Okay, it's not very complicated, but it's a very ingenious construction. I recommend you to have a look at the paper. That's really cool, because it tells me that in order to prove self-testing in the non-IID case, all I have to do is to find a linear witness. You have to find a linear witness such that with this property, right? I mean, if for any distribution that I can generate with d-dimensional quantum states and measurements that is close to the maximal value, then I should be able to prove that there exists a unitary or anti-unitary, such that the states that generated the distribution are related to the reference states by conjugation, and the same with the measurements. Once I'm here, then I can use the results of these people in order to devise some statistical tests to self-test these kind of things. Okay, so this is what this paper shows. If you give me any number of pure states and any number of extreme POVMs, then I can give you some pre-parameter scenario with more or less the same amount of preparation, more or less the same amount of measurements, and a linear witness with this property. In this, well, we're writing a sort of note. It's kind of trivial things, but there are things that people are kind of ignore or something. If you drop the IID condition, you cannot self-test state ensembles that include mixed states or POVMs that are not extremal. So this means that this result completely solves the self-testing problem in the prepare and measure scenario. It tells you what you can self-test and what you cannot self-test. Okay, so let's see how it works. I'm going to give you some, to give you actually a pretty detailed idea of how it works, why we can self-test everything essentially. Okay, the basic idea is this witness. Suppose that you give me some pure states that satisfy this property. Okay? That there's some linear combination of them with positive coefficients that is equal to the maximally mixed state. Then I can think of this scenario. This is a prepare and measure scenario with n preparations. And yes, of order n squared measurements. And intuitively, okay, there's a measurement for each pair of states. And intuitively, each of these measurements will try to best discriminate these two states. This is intuition. Okay, now I'm going to define this witness. This is a witness, of course, that depends on these things, but it is linear. It is linear on the probability, right? In case you wonder, this witness is a variant of some dimension witness that appear in this paper. This year is the jubileum of this witness. Okay, so I claim that the maximum value of this witness for d-dimensional systems is 1 minus 1 over d. And also that if you saturate the bound, then the overlaps of the states that you prepared are equal to the overlaps of the reference states. So we're going to see why this is the case. So the first thing is to make what you call a vector of differences, right? I mean, you get any ensemble of pure states, and then using these positive numbers, then you create this vector. And I'm going to give an upper bound on the norm of this vector if these states are actually d-dimensional. Well, so I substitute the definition. Now I use some inequality that relates the trace norm to the trace of the products. And I note that any pair of pure states saturates this inequality. Okay, so this will be important. Okay, so you replace this thing. The next step, you just eliminate this dependence of the indices, right? I mean, make them independent, split them. Use this property, the fact that all these numbers have to add up to 1, which follows from taking traces here. And then you end up with this. And the only moment where you make use of the fact that these things are d-dimensional is here. So here you have a state. This is a quantum state, it's a normalized quantum state. And the trace squared of a normalized quantum state is lower bounded by 1 over d. This is the only thing. So this is called the purity, right? I mean, states cannot be extremely non-pure in the dimensions. You substitute and then you get the upper bound. Okay. So, of course, if the upper bound is saturated, all the inequalities that I wrote before were tight. And in which case, if you go backwards, but which I cannot imagine that, but because it's a bit too much information, right? I mean, but the important thing is that if the states are pure states and they satisfy this inequality, then you can show that the upper bound on the norm of this subject will be saturated. And if it's saturated, maybe they are not pure states, right? I mean, not necessarily, but they will satisfy this constraint and this other constraint. Okay, now I can prove the claim. So we start with the witness. This part here, if you write it in terms of prepared and preparations and measurements, it's just this, which of course is bounded by the trace norm, of the difference of these two states. And actually, this bound is tight if you choose the measurement appropriately. Okay, so you get this. But notice we know what it is. This is simply the overlap between two difference vectors. The one corresponding to the reference states, and the one of the states that you generated this distribution. Now use Cauchy-Schwarz. Use the fact that the value of this thing is equal to this expression. The maximum value of this thing is equal to this other expression, and then you get the upper bound. So it's not very complicated. It doesn't rely on sophisticated mathematics. All you have to do is to connect many. Now, of course, the self-testing. If you saturate the upper bound, all the inequalities are tight. And that's really cool, because if this inequality is tight, then it means that these two vectors are parallel. If this inequality is tight, this one here, it means that the norm of this vector is equal to this one, is the maximum one, and these two things together imply that these two vectors are the same. So it's really easy, right? I mean, now use the fact that because this thing has maximum value, which is the only way that it can be maximized, right? I mean, the inequality. Then you have this relation, and now you compare the two values of the coordinates of this vector. Oh, it's very complicated to get the. I'm pointing here to get the pointer here. Not easy. I'm going to move up. Okay. Ah, okay. No, here is fine. Yeah. Okay. So.
Smart pointer.
More than me. Okay. Yeah. So with this thing, you already have that the overlaps for different states are the same. They have to to be the same. And the only thing that rests is to show that this also holds when this index I is equal to j. You have to show that these states are pure. But this follows from this relation here. If you take squares and then take into account that for non-matching indices you have this identity, then you end up that you realize that the only way that this can happen is that all these traces squared are equal to 1. So everything is everything. So this is the claim, okay? So again, repeat. Whenever this witness is this witness is bounded by this expression, whenever it's saturated, then you have the same overlaps. This gives you a very simple method to self-test state overlaps. So you give me some, you have some pure states, and I want to self-test that the states in my experiment have the same overlaps. Okay, so what I do is to come up with some other states, some other pure states, such that there exist some positive numbers, such that this holds. These are very easy to find. I'm not going into detail. Then you construct the witness scenario, and of course, if this holds, if you get the maximum violation, which you can get in principle, then you know that the overlaps will be the same. Okay. Now, the question is whether the fact that the overlaps are the same implies that the states are the same, modulo anti-unitaries. Okay, if you think about it and you have studied physics, then this will remind you of Wigner's theorem. Wigner's theorem is something that you learn when you study particle physics. It is some theorem that is used by Wigner to classify physical symmetries. It doesn't really matter that thing, right? I mean, what matters now is what it says, right? I mean, it simply says that if you have some map from rank 1 projectors to rank 1 projectors that preserves the overlaps, then there exists an anti-unitary transformation that implements the map, right? For a unitary map. This is exactly what we need, because in our situation, well, it's kind of the same. It's not just pretty much the same, right? I mean, in our case, the map would be simply a map between some set of states to another set of states. So it's not defining the whole set of all possible rank 1 projectors. What we want is this, right? I mean, you have some set of states and some other set of states with the same overlaps. Can we conclude that there's always a unitary or anti-unitary transformation relating the two sets? And in the paper we show that this is only true for dimension 2. In dimension 2 this is true. In dimension 3 we already have counterexamples. Actually it's cool. In the paper we show that if you take 3 random pure states in dimension 2 and then you embed them in dimension 3, then it's not true.
How big are the sets of the points you're looking for?
Or their
PIs,
or the
I mean.
D, or the D.
Or the D?
Yeah.
Because of course, if it's true for all finite rank projections, then it's Gleason's theorem. There's another theorem.
Okay, it's true, it's true.
Yeah, so it depends a lot on how many points you test.
Yes, indeed. And actually that's the way to solve it, right? I mean, well, we didn't go to Gleason, but we went to the proof of Wigner's theorem. If you go to the details of the proof, what the standard proof, what Weinberg does, because actually Wigner didn't provide a proof I guess for him it was intuitive or whatever, right? But then in the Weinberg you can find a proof. And the proof, it tells you that if you define the one rank projections of this set of states, then any set of states, you take any set of states together with this one, has this rigidity property, that any other set of states that have the same overlap have to be related by a unitary or anti-unitary. Okay? The only problem with this is that this is it's a tomographically overcomplete set, right? I mean, it's a really large set. We like something a bit smaller, so then we want to. People keep making proofs of this theorem. I don't know why. I mean, there are lots of proofs in the literature. It's I don't understand what the point is, but they're getting shorter and shorter, and it's cool, right? I mean, and in this one they managed to do the same, but with only of these states. If you get to the details of the proof, right? I mean, you won't find this in the statement. And the only thing is that the states have to satisfy this constraint. They have to be have non-zero overlap with the elements of the computational basis, and that's all. Okay. So now, how do you self-test? How do you say information to self-test pure state ensembles? You give me some set of pure states that you want to self-test, and then I'm going to do is I'm going to add this set E of states, but I'm going to rotate it with a random unitary to make sure that this condition is satisfied. Now I'm going to add some other states such that there exists some positive numbers such that this holds. And once I'm there, then of course I construct the witness, and of course if the witness is maximized, then you get that the overlaps are the same, and by this version of Wigner's theorem, we know that there exists a unitary that is relating them. So you see, it's not that complicated, yeah.
So Do you have to assume that the psi axis without the bars on, the non-ideal states, that they're in the same space of the same dimension?
I didn't understand the first part.
The psi axis, do you have to assume that they're in this in CD?
Yeah, sure. Yes, yes. Yeah. Okay. Okay, so that's how you self-test pure states. Now, how you self-test POVMs. Okay, you already know what a POVM is. An extreme POVM is what you would imagine it to be. Okay, it's a POVM that you cannot express as a convex combination of other POVMs. The problem with this definition is that it's not very useful, because if I give you just a POVM, how can you argue that you cannot express it as a convex combination of other POVMs? It's very natural definition, but it's not very practical. So that's why in 2005, these people, these three guys, found a practical way to checking if a POVM is extreme. All you have to do is to decompose it like this, and you have to make sure that all these operators are linearly independent, and that's necessary and sufficient. Now, another way to put it, and this is the way that I'm going to use, is that for all set of matrices that are also d-dimensional and with support containing the support of each of the MBs, the fact that the sum is equal to 0 implies that each of the elements is equal to 0. It's equivalent to what I just said. That's really cool, because with this I can prove that extreme POVMs are exposed, which to my knowledge was not known, but okay, it's not that complicated either. But I want to use it, so that's why. Okay, so suppose you give me some POVM. Now I'm going to construct a projection to the kernel, and then I'm going to define an optimization problem. It's an optimization problem of the set of all POVMs. And I claim that the solution is 0, and the only minimizer is M. Now, it's pretty clear that this thing has to be optimal, right? I mean, because this thing is positive, right? I mean, it has to be greater than or equal to 0, and because this thing is a projection to the kernel, this is equal to 0, right? I mean, so clearly this M is optimal. You have to show that it is unique. Now, it's unique because if you assume that you have another POVM that has the same value, then of course, because of positivity, it means that each of these traits is equal to 0, which implies that the support of this thing is living in the kernel of the set B, but because of the way I define it, this is the support of MB. And now I define this matrix. I take the POV that we're testing against the one that I know is optimal. And of course, by definition, the support of this matrix will be containing the support of MB. And now if I add up all the B's, right, I mean, because all these things are normalized, I get 0. And then I invoke the extremality of the POVM, right? If this happens, it means that LB is equal to 0, therefore MB is equal to MB tilde. Okay? So this is how I self-test an extreme POVM. You give me the POVM, then I construct these operators, these projectors onto the kernel, and then I diagonalize them. And now I consider the pure state ensemble given by these pure states, plus this set, plus some extra states to enforce that they're equal to the maximally mixed state. And now what I do is to define this witness, the one that we had before, the one that self-tests these states, minus this other thing, this other part. And now this other part has is smaller than or equal to 0, and this part is bounded by 1 minus d, so the whole thing is bounded by 1 minus d, 1 over d. Okay, so what happens when you saturate the inequality? When you saturate the inequality, the only way to do it is that this is equal to the maximal value, this is equal to the maximal value, right? In this case, we know that we can self-test the states. There's a unitary or anti-unitary. If we apply the same anti-unitary on the POVM that was generating the statistics, generating the P, then we get this relation, but we know that the only solution of this problem is that M tilde is equal to M bar. So that's how you self-test an extreme POVM. So far, I've only been speaking about how to self-test things exactly. In the sense that I didn't allow any noise, right? I mean, I show you that if the linear witness is equal to the maximal value, right? I mean, then you have this property, right? Of course, you can prove that some robustness results. I'm not going to get into how to prove it. When I read this part of this work, I thought that this part would be very tedious but very straightforward, right? I mean, just going through the exact proofs and then trying to make an error analysis. If you do that, you will get really terrible bounds. You get like some towers of these, right? I mean, it's really terrible. So I don't recommend you to do it. It was a surprise to me. You need a bit of creativity to get bounds that are only bad but not horrible, right? I mean, these bounds are horrible. I'm going to show you how to get the ones that are bad. So to get well, I'm not going to show you. I'm going to tell you the techniques, right? I mean that we use, right? I mean, and it's a long proof, right? I mean, I don't want to get into it. One of them was the pretty good measurement. This is a measurement emitted by Waters. It's called also the square root measurement. And it is that if you have some states which are almost orthogonal, then there is an orthonormal basis that almost optimally discriminates them. And the reason to work with this basis, with this square root measurement, is that mathematically it is very easy to describe. So it's very easy to use it to get bounds on the right? I mean, that plays an important role. Without it, you will get these exponential towers or something worse. Another thing is that that avoids you a sort of exponential tower of this is the fact that you can solve three diagonal matrices. A matrix of this form, okay, where I mean all the elements of the diagonal are the same. Maybe you can also change the ones on the ends, right? I mean, you can also change these two here. These things you can diagonalize them exactly. Okay, and this we used, right? I mean, using what computer scientists called usual methods, and I don't know exactly where they get it from, but it appears in many proofs actually. Yeah? And the third one is SDP duality. SDP duality, well, probably you know about this, right? I mean, a semi-infinite program is a program of this form. It's a linear optimization over positive semi-infinite matrices that depend finally on the variables x of the problem. And the dual is another problem that you can also write in this way. It's a maximization problem, and the solutions of the two problems coincide. And in the proof of in the analysis of errors, I'm constantly making use of this kind of ideas, right? I mean, all the time. They're like 10 times or something like that. It's a very long proof, really. I don't recommend to follow. And this is the result. The result is really cool in D, right? I mean, you don't get any explosion of D, but the exponents that you get are terrible. These are really, really bad exponents. In the case of D equals 2, you don't get, things are not that bad because you have Wigner's theorem generalizes, right? I mean, immediately, you don't have to introduce these extra ancillary states. But if not, yeah, 1 over 32 makes these bounds completely useless. Okay. The reason, I don't think this is really I don't think this is really a problem of the witness. I think it's a problem really of the error analysis. The proof that we have in the paper is human generated. And because it's human generated, we follow the Cartesian way of dividing the problem into small parts and then connecting them, right? I mean, it's what all of you do. But the problem is that when you do error analysis, it has a cost. And to go from some bound on the maximum value, right? I mean, some epsilon approximation to the maximum value to some bound on how close the overlaps are, then you incur in a penalty of a square root. To go from this situation where you know the overlaps up to some approximation to a situation where you actually know the states up to some approximation, you have to go to this horrible thing that we have in the paper of a robust version of Wigner's discrete theorem. It has 3 parts, so you get 3 squares of root, 3 square roots, so you get 1 over 8. And to go from, once you know how to self-test the states, you have to use this knowledge to self-test POVMs, but then you get another square root. So you put all of them together, you get 1 over 32. It's really terrible, but I think it's just simply the way we prove the thing. I don't think it's really related to the witness itself. Wow, I finished really fast. Okay, so the open question, the most pressing one for me is to improve this robustness bounds. I think that maybe with some high-level analysis on convexity, maybe you can prove that these bounds, the optimal bounds can be proven approximately convex, for example, right? In which case you will get you will be able to get linear bounds. Maybe that will be the way to go. Another possibility is to use semi-infinite programming for particular cases. Normally, when you conduct an experiment, you're working with a. Has anybody worked with an experimentalist? Do you know what an experimentalist is? Okay, so normally when the experimentalists they don't know what to do with their devices, the motivations are completely different from the theories. They want to experimental control, right? And then, but they want to get also some sort of proxy for experimental control. They want to show that they control the experiment better than the people from the lab next door. And then they want theories to give them like some sort of thresholds or test beds, right? I mean, so one of the thresholds could be to do a self-test. But normally they want you to self-test concrete things, right? I mean, so they will tell you, look, I would like you to tell me how to self-test this set of states. If they tell you that, then you can use some techniques that I didn't reference, right? I mean that I and some other people developed based on semi-infinite programming that allows you to get possibly much better bounds than the ones that you can get analytically, right? I mean they are numerical, but they're still rigorous, right? I mean this is the way I would go. Yeah, in the conference dinner you can buy me for some drinks, and I will tell you some other things that I about experimentally, but I not the stuff. Yeah.
So your error bounds are not good enough for the position they can produce. Is that the problem?
No, I think this is terrible because because then
They can only 30.
no, but 32, right? I mean the noise that you would have to have is like further 10 to the minus 10 or something like that. It's really challenging for experimental.
Right. Okay.
Yeah. It's possible that actually if you go to the exact analytic bounds that you can also find in the paper, which I didn't do, it doesn't look that bad because of the prefactors, right? I mean, maybe it's not that terrible. Yeah, this is just another of magnitude, right? I mean, I don't know. Yes, I don't know. Okay, another question that I have, I think it's an interesting geometrical question, is given some set of pure states, how many states do I have to add to this set such that I get a rigidity result, such that any other set of states that have the same overlaps are actually related by unitary or anti-unitary transformation? I think this is a nice question, a funny question. For d equals 2, the solution is 0. You don't need to add anything. For general d, at least well, okay. If you add this d states, right? I mean, that's enough, but I could believe that in some cases it's enough to add 1 or 2, right? I mean, actually, it's easy to come up with examples. I can give you the set E that I gave you before and subtract 1 state, and you have to add only 1 state, okay? I would like to have an algorithm to tell me these things, and probably the experimentalists also would like it, right? I mean, because then they could be able to test concrete ensembles. Another question is how to extend these ideas to other scenarios. Like there's a scenario that where you can extend these ideas easily. We have 3 parties: Alice, Bob, and Charlie. Alice prepares, Charlie measures, and Bob transforms. He conducts some channel here. In the particular case that this channel is unitary, then I can show you how to self-test it using exactly these ideas, because essentially it's a problem of state estimation, right? I mean, the moment that this channel introduces some noise, you become problematic. You may be able to find some protocol to self-test channels that are maybe not unitary, but extreme, right? I mean, there are extreme channels which are not unitary. Those would be interesting to see. And I'm going to stop here. Thanks.